Hello to you all. I'm happy to be here to present the second half of this day. And the next project that's going to present is the Action Project, will be presented by Anna from Imperial. Anna, the floor is yours for Action.
Thank you, Jerzy. I'm here behind you. And I also want to thank the ACT sponsors in advance for making this project possible. We started a little bit later than everybody else. We were in the reserve list and we had to go the extra mile to secure the UK funding. And we were very lucky that a number of industry partners have come forward with funds to support our activity, so we are very grateful. And our project is, as you can tell from the title, is looking at developing an advanced multi-temporal model and optimization tool for CO2 transport, storage, and utilization networks. And we have partners from 7 countries that are spanning continents, many time zones, but not very many that it is impossible for us to meet. The Imperial College is the coordinator where I come from. And some of you know me, I have been in CCS business for a very long time. I was just discussing with Ragnhild since 1997, having met Tore Torp from Statoil then, and also Lars Stromberg from Vattenfall, when everything was happening in CCS. So in this project, besides ourselves, we work with a number of excellent colleagues whom we again know for a very long time. Philip Niele from TNO is here. He is responsible for our WP2. I will talk about it in a moment. And then my colleague, Professor Durucan, you have seen already with his vast experience on the CO2 storage side. Alongside colleagues from the University of Alberta in Canada, from Los Alamos National Laboratory, from IFP Energy Nouvelles in France, and GeoEcomar, we are the R&D research institutes that are conducting the core of the work. And you can see above the world map the industry partners who are supporting our work as core partners of the consortium. And then we have 7 associated entities who are also participating in our project. So we are in total 13 partners and 20 overall with our associated partners. We started on the 1st of February, as I said. We will finish at the end of January in 3 years' time. And in line with the request, I have to explain the vision of our project and why we are doing this. Obviously, the objective of the ACT program is to accelerate large-scale implementation of CCS and CCU. And to do that, we need to have an available and flexible utilization of a transport and storage network. Now, to be able to have that, we need to be able to handle variable supply rates of CO2 that may be coming from a number of different sources, and also to avoid having to incur potentially emissions and costs because we have to vent. And in our project, what we are trying to do is to support with the development of our tool the objectives of the network operators who are looking at the overall cost of storing or the benefit of utilizing the contracted amount of CO2. And we have to respect, from that point of view, complex engineering, economic, and regulatory constraints, which might be different for the different operators at different parts of the value chain. And if you think from the point of governments or regional regulators, we have to consider the strategic decarbonization viewpoint. And from that point, we need to see that the system that we have in place allows us to have optimal performance, not only at operation level, but also at cluster level. In the work that we have been doing until now, we have been trying usually to match sources and sinks, and trying to do that having in mind a long-term time horizon, say the 2050 or 2040 targets that may be set in different regions. Now, to do this, we have been working with quite coarse models that had a reasonably large time step. And what we want to do in our project is to actually reduce those time steps and go from something that might be at operability level very fine, or at strategic decarbonization level, an annual or a multi-year or a planning horizon resolution, and in that regard, be able to also support the operators and also the regulators to confirm how much CO2 is being avoided or stored, and to do the reporting accurately, so we can see that actually we are progressing with our decarbonization agenda through this activity. And in that regard, the way that we are going to meet our objectives is by establishing how such an efficient infrastructure that connects the sources, the geological storage sites, and the utilization options are as part of decarbonization efforts. And we are going to develop this multi-temporal integrated assessment model, which we will make available. And we hope that it will support stakeholders in the planning of large-scale, flexible CO2 transport, utilization, and storage networks. But it also is going to enable us to do the reporting while addressing engineering, geological, economic, regulatory, and environments, as well as the uncertainties that come with all of this. So in this project, you will see over the years, as we are progressing, we are using a term that we have introduced in our proposal, which is the term multi-temporal. And what I wanted to do up front is to explain what we actually mean by multi-temporal. So in our project, we have 3 different temporal resolutions that we are going to be doing work. In the short term, that covers hours or days, this is the resolution that we are using to confirm that we are operating safely and efficiently the network, and to enable the utilization options, which might be, at least in the early days, at much smaller volume, and maybe even at intermittent intensity. But then to be able to couple the network with how a storage site operates, we need to consider a medium term, because the reservoirs operate in that resolution, or react in that resolution. So we have to have a part of our modeling that addresses the dynamic storage capacity and links up with the large-scale transport and storage network that has these multiple storage and utilization sites. And finally, for the long-term horizon planning and decarbonization targets, we have to work with a long-term a temporal resolution that is focusing on several decades. The structure that we have in our project contains 5 work packages, plus the project management and dissemination activity that we lead at Imperial College. So our colleagues from IFPEN are responsible for the WP1, which is looking at the development of engineering and geological proxy models. And I will try to give you a deep dive on some aspects of what we will be working on in the coming period in the next slides. Then our colleagues at TNO are leading the second WP, which is focusing on transport network operability and the multi-temporal CCUS model development. Our colleagues at Alberta are leading the project in terms of extending what has been the risk assessment studies that have been following solely either on storage or wells, or sometimes storage and wells related aspects, to actually focus now on the integration of storage and network risk dynamics. Then our colleagues from the US are going to focus their efforts on the development of CCUS proxy models, which are the equivalent of the geological storage models that we will have for other parts of the system and the transport parts of the system in WP2. And then at Imperial, we are going to work on life cycle assessment and life cycle costing. And again, I'm going to try to give you a flavor of this work. And finally, for WP5, we are going to have 6 strategic decarbonization scenarios, case studies, regional case studies, where we are going to test the tools that we have, would have been developing in the different work packages, and the overall tool integration that we are going to make as a result of our project. And to show you a little bit more about what is inside our project, Obviously, over the long period that we have been working in CCS, many of us, also including a lot of people who are not in this room today, we have been working on geological modeling and CO2 storage engineering models development. And what we want to do in this project is not to forget what we know or redo what we know, but instead, based on this knowledge that we have had on a number of different sites that have different characteristics, and they might be depleted fields, CO2 EOR sites, saline aquifers, use all this knowledge and through the development of proxy models, go past the demanding engineering workflows and also capture through sensitivity analysis and optimization under uncertainty, what is important in the different geological systems that we may have at a number of sites that are connected in one transport network. So you can see some examples of those sites in the previous slide, and here all of these sites are across the North American and European continent, as you would have seen in the slides. And in our different subtasks, you can see them in blue color here, are some of the sites that we already have detailed modeling work carried out by the project partners, and we are going to be utilizing them to develop the specific proxy models. Now, this work is mostly going to happen in the first year of our project, in the early period where we are going to be doing this testing. And what we have to consider is that we have to interface all these models together in our multi-temporal system. So we have to decide what are these key KPIs that allow us to connect the important features of the geological systems, as well as the way that they are being operated in order to perform the function of CO2 storage. And those of you who know us, you would remember from the past years, we have a lot of experience working in Sleipner, at Insala, on a number of depleted gas fields and saline aquifers here in the Netherlands, in the North Sea, in Norway, and our colleagues from North America also at a number of different sites. And then we also have GeoEcomar from Romania, who are also going to bring their expertise, and we are going to help them also improve the work in the Getica project. Now, I know I have to run fast, so Gerd is also already warning me that I have to speak about our transport network, where we are going to develop a pipeline, as well as shipping work and a multitude of emitters. Now, our colleagues from TNO, and I have to apologize that I am not going to do justice to this work. There is quite a lot of effort that is going on the development of the proxy models and the validation against base models that we have in commercial tools that those of you who work in transport would know, such as the Olga system. And from Align CCUS, benefiting from the work that we have done there in shipping, we have already started enlarging this activity, considering the Stella Maris concepts. And I was taking notes yesterday from all the good work that was being presented for the extension of the different European value chains, also including onshore networks development. And we hope that overall, when we bring all the system together, we are going to be doing this in what is called the multi-agent optimization tool, which is an introduction that is for the first time in the CCUS area. People use this type of tools in electricity networks modeling. So we are going to be testing this, and the reason why we are doing this is because all the different parts of the system, say the capture, the storage, the utilization, hydrogen production, and even the transport system, they operate quite differently. They have different physics, different temporal resolution, and to bring them all together, we need something that can be configured to respond to this type of interaction required. Okay, so on the network risk dynamics, we have to integrate the storage and the network aspects. The first task that we have started already working on are the key performance indicators, and our colleagues from North America have begun this work. And on the CCU proxy models development, we are focusing specifically on power, steel, and cement industries, as well as the development of models for utilization and conversion technologies that you can see in colorful purple and yellow texts there, and you will be able to see in our slides when they are distributed. And we are going to integrate those in a life cycle costing model, which we have been developing for many years at Imperial College, and is what is called the ICLCA model up here. And our colleagues at IFPEN are going to work on the consequential LCA framework, which again is going to be a new element that we will have in CCUS. And we will have 6 regional scenarios. Each of the countries that is collaborating in the project is going to work on those. And right now we have only had 4 months, so we are very early, but still making very good progress. We have a website that is functional, and you can go and learn a little bit more about our project. And we will be grateful if you come and visit our poster when we are at GHET in the autumn. And we look forward to hearing from you with any questions, either later today or at some other time. And the last but not least is to thank the ACT sponsors for enabling our project. And thank you very much for your attention.
Yes, Anna, thank you very much. This was really very impressive and well done. I wish you a lot of success with the project. But we go on with the next speaker to make sure that we stick to the time schedule. Our next speaker is also talking about a subject related to storage and wells, in particular reuse of existing wells. Maartje, can I invite you to the stage? REC CO2, ladies and gentlemen.
Absolutely, thank you so much. Let me see if I understand this technology. I'm Maartje Koning. I'm project manager at TNO. And also for this particular project, I'm leading the different work packages. So we've already heard a lot about all the different CCS components. Today I just want to give you a very high-level overview of the work that we've been doing that's focusing more on what's happening underground, specifically looking at the wells, looking at existing wells and how we could actually reuse those for CO2 injection. Too fast. But what is REC CO2? Oh, wonderful, see? This is my very first conference in many, many years, just seeing everyone out there, it's great. What is REC CO2? Again, it's a very nice acronym for reusing existing wells for CO2 storage operations. And like most of the other projects presented here, it's an international research project. We're funded by the second call of ACT. And it's actually spread across quite a lot of different countries. At the moment, we are covered by 6 different countries, mainly within Europe, but also the US is taking part of this. The consortium is quite wide, and I think it's a really excellent combination of different R&D institutions, branch organizations, national authorities, but also operators, industry partners who are part of this. In total, we have 19 partners within these 6 different countries. And throughout the project, because we're almost nearing completion already, we started in 2019, we have actually gained a lot of momentum. And a lot of industry partners, particularly industry operators, are actively approaching us to be part of this project, or to see how they could actually use our developments, our tools for further assessments. So we have gained 3 new partners, 2 industry partners and 1 R&D partner on material selection, and that really, boosted the consortium, made it even stronger. You can see all the logos of the partners participating within this consortium. I'm absolutely not doing justice to all the details that people have been working on in the last 3 years. We do, however, have all of our deliverables made publicly available on our website. So if you haven't done so, please go and have a look. There's a lot more information, a lot of details, and very interesting stuff to read. What was driving REC CO2? It's really about the motivation is to facilitate the CCS in depleted oil and gas fields. We do see a lot of fields approaching their end of field life, looking at enormous costs for decommissioning, plug and abandon your wells. So there is a lot of material, a large portfolio that could potentially be reused for a different purpose. And that's exactly what we wanted to assess, is how can we actually look at this enormous amount of, particularly the wells, so not the facilities, but the wells themselves. How can we look at them in a structured approach, systematic approach, and help people who actually need to make decisions, the industry partners or industry, the operators, the regulators, with a way to say how to move on and if they could actually be reused. So the objective at a relatively high level for our project is really to develop such a method for people to look at their well stock and see which wells can be reused and which wells to spend a little bit more time on. And at the time that we started, there was no such tool available. So we were very much the first ones to actually look into this problem and to identify and to make this kind of workflow available for people. And again, this is also something that will be publicly available on our website. Again, just to recap, and I think it is really important to mention, we really want to make sure that we provide the decision makers, so the industry people, the regulators, with a mechanism and the right information to properly be able to evaluate repurposing or reuse potential of their existing well stocks, being gas producer, oil producers, and so on. And we do that through different pillars within the project, all led by different people within the consortium. In short, the main core of the project is really about the development of a tool, a well screening integrity tool that has been worked on by TNO and Lenel to really start looking at the wells themselves and whether there is a potential risk for leakage along the entire wellbore. This is all within the legal frameworks of the national, the countries the nations that are part of the consortium, and also is run in parallel or is supported by, supported by experimental work where we really start to look at different components or fundamental questions that have to do with well integrity and how to identify that. The tool by itself is being used on different case studies, and I will show you a couple of examples of that, to really come up with all in total, so including the framework, the legal aspects, the laboratory experiments, but also the case studies, to come up with best practices recommendations for how to actually reuse the existing wells for potential CO2 storage. So it's quite an extensive scope that we do. So how does it look like? This is just an impression of the tool itself. So again, it's a very easy to use, intuitive tool that we have developed, which runs through a well-by-well approach. And it basically goes through a whole set of different questions that as a user you have to address or have to answer. And they're all linked to the different components of well integrity, going from the reservoir and the cap rock, so basically the rocks that penetrate the well, but also looking at the well construction and the history. How was it actually built? How was it completed? And also looking at the integrity record. What kind of issues that we might have with corrosion of the casing or corrosion of cement or any other issues. So it really tries to structurally identify whether there is an issue with one of these components, yes or no. And the way we do that, you can already see that a little bit on, is that working? Yeah, awesome. In color coding, we really like to make this visually attractive as well, so that you can right away see green, yes, that means good, red, attention. At the end, we, after each of these assessments, there is a recommendation that basically wraps up everything and explains a little bit on what kind of issue you might have in terms of integrity with the particular well. The final results at the end, again, are like, a traffic light system, very self-explanatory, and it goes through the different components of the well integrity, color-coded. And as you can see, ooh, man, my kids would be so much better at this. Where is the dot? Well by well, you can see, well, it's all red. That means there is a serious issue, critical. You need to do severe remediation to your well to make this actually a CO2 compatible well injector. There also is another category, gray, which basically means there's a lack of data. And this is what we found, that a lot of data sometimes is missing, at least in the public domain. So what's underpinning these nicely looking questions is actually a complex set of 5 different decision trees, which all focus on different components of the integrity part. You see them down here: out of zone CO2 loss, structural integrity. We're looking at primary and secondary well barriers, and also material compatibility. So the CO2, how does it respond to the steel, to the cement, and to the rocks? And this is just a screen capture of how that actually looks like and how the logic works going from one question to the other, because depending on what the user actually fills in per question, you will get another set of questions that will directly direct you to the proper, the proper assessment. We wanted to make this that it's relevant for any well design, being onshore, offshore, no matter what kind of type of completion you have, subsea or whatever. So it's very much applicable to a very large range of wells. So we have tested this tool on a whole set of different case studies. Here a couple of them are mentioned across Europe, but also in the US. What we tried to do is to use a very wide variety of test cases to see the applicability of the tool and not limit ourselves to just only one type of case. Looking at onshore, offshore, different fluids, in situ fluids, different depth, different geology, but also different capacity, so size of the amount of CO2 that could be injected, and also lots of different wells. And overall, so the one that I highlighted in green on the top, I think that's important to mention, is that this particular one was used as a benchmark, because next to our using our tool to do the assessment, to do the screening for well integrity, for risk potential, for leakage potential, we also did a engineering assessment, so a really manual approach, looking at these wells one by one, very intensely, and basically the results were very much in line. They were very similar, which to us showed the application of the tool itself doing quite a good job. I think it's good to mention that any of these test cases we did in very close collaboration with the industry partners. So there really was, the end user perspective was taken into account on how this tool should further develop, what can we do with it, and how would it actually help them to risk mitigate. We also looked very briefly at a high-level cost-benefit analysis to really see what would be the cost implementations of reusing the wells instead of abandoning things. I mentioned before, in parallel, we also kicked off an experimental design, and this was basically done in about 5 to 6 different places across the world. And what we tried to do is really to answer some fundamental questions that have to do with the integrity part of the well. So how, for example, well degradation and the well design actually influence potential reuse. So instead of using it as a hydrocarbon producer, if you want to use CO2 injector. We're looking at self-healing leakage pathways, microbial remediation, a whole lot of different components, but really to define boundary conditions at which well integrity could fail or be remediated. And again, there is so much more work done that can't be summarized in 10 minutes here. So what I'd like you to take away, at least from this presentation, very high level, is just a couple of things. What we believe the value of REC CO2 at this point in time is that we see at a very early start of looking at your well stock for potential reuse. We have generated a tool that allows you to do a very fast turnaround time and make it very systematic approach to assess a very large number of wells. And by doing so, we think we can actually improve the decision making, because very early on you know which wells could potentially be reused and which wells could not, which leads to optimized capacity planning and hopefully also cost savings by not having to spend a huge amount of abandonment cost, but instead repurposing those wells. And at the end, hopefully this will lead to facilitate the safe well reuse and hopefully CCS uptake. I hope I have half more minute to go in more detail on the case studies. Again, I mentioned our tool, we believe, is very much in line with a more manual engineering assessment. We also see that all of the wells that we have assessed do need some form of intervention to make them ready for CO2 injection. From the experimental side, I think important to mention is that we just started with the beginning. We need to develop a much larger database, particularly of downhole conditions, to be linked to the experimental work that we do to really upscale from the experimental work to the well scale. Permitting, I didn't really touch upon a lot of it, but it was a very important part of the project, where we see there is a lot of difference in permitting to apply for CO2 injection, and there's a lot of differences going on across in different countries. What we do see as one of the most important part is that there is a large, there could be potential barriers in the time gap of end of production of a field and CO2 injection uptake. And it's really important for anyone who is involved, so the operators, regulators, but also future CO2 storage injectors, to start the discussion, to use the tool to evaluate the wells, share data, but really have the discussion on how to move on and see if there is a potential for reuse of these wells. And with that, I would really like to thank our funding agency and everyone who made this happen. And yeah, looking forward to closing off the project after the summertime. Thank you. Not sure if that allows for questions.
Yes, well, thank you very much, Mike, but well, time is running. The situation is that we do have a little break between the next presentation and the usage session at 3 o'clock. So maybe if you keep your questions until the end of the CEMENTEGRITY presentation, then we can have a short session with questions to Maartje and Anna and the presenter of CEMENTEGRITY, whose name is Goethe Swenningsen. Goethe, are you here? Oh, you're there. Now we have a presentation from CEMENTEGRITY project. It's an Act 3 project, so it's recently started. And Goethe, the floor is yours.
Thank you. So good afternoon, everyone. It's nice to be here. As many have said before, it's nice to get started again after the pandemic, meeting people, having a drink, perhaps in the evening. So yes, it's very good to be here. So I am Goethe Swenningsen. I work at the Institute for Energy Technology. We are located outside Oslo in Norway. I'm actually here on behalf of my colleague Rainier van Noort. He was not able to come, so he sent me instead. Rainier is more an expert on cementing and reservoir and so on. I am an expert on corrosion and material, and we have a lot of projects on the transportation part of CCS, where we study chemical reactions and corrosion. But I will try to cover this project. Our main motivation in this project is to ensure that the wellbore remains tight, that it has a good integrity over the whole duration of the whole lifetime. And we know that cementing has been identified as an important potential weakness in the system. And just imagine this, you have found a perfect reservoir. It's huge, you can store an enormous amount of CO2 in it. And you spend millions and millions and millions on investigating it, doing the seismic study and so on. And what do? We drill a hole in it, a lot of holes. Of course we have to do it because we need to inject the CO2. But it's also an obvious weakness for leakage. The cement seal has been identified as something we need to study, and it has been asked for experimental studies and verification of that the cementing can maintain a tight wellbore. So I think we have already seen some in the previous presentation, some a list of where can we have leakage. This is in this picture. It's a well that has been plugged. So there is a cementing in the bore. Of course, there's also cementing on around the casing. So we might have leaking, of course, through the cementing. It can be along the interfaces. You might have corrosion and creating holes in your casing, and so on.
I think you can also point at this one.
So there's a lot of different pathways for CO2 to leak out. And what is perhaps important to acknowledge that in a CO2 well, there is slightly different conditions compared to oil and gas well, because you have really, really high pressure of CO2 that gives you a lower pH, and there is also some impurities in this CO2 that can react chemically and create strong acids. For instance, we have shown that you can form sulfuric and nitric acid in the CO2 if you have NO2 and SO2, for instance. So our project was just recently started earlier this year, and we have a number of partners, IFE from Norway, Halliburton and the Norwegian part of Halliburton, the Technical University of Delft, the University of Stavanger, IBM, Heriot-Watt, Restone, and Wintershall. Since we just started, I have not any results to present, but I will try to give an overview of what we are planning to do. So we will have seven different work packages, and they are intended to be fairly linked together. So there shall be no large walls between these work packages. Everyone is supposed to work together. And we will try to, as good as possible, to have information exchange between these work packages. We have identified 5 different sealants that we will use for testing. As I said, I'm a corrosion expert. I'm not an expert on cement or sealants. But there is some description of the sealants here. And as I understand, the first 4 are fairly classical cement. But we also have a geopolymer that is being developed in this project. And we will have a lot of these being prepared by Halliburton, and they will provide cement and sealant samples for us to test. So the first work package will study the effect of gaseous and supercritical CO2. It will be led by Halliburton, and they will use various techniques to study cement and how it is affected by CO2. For instance, they will study the permeability and use some kind of micro indentation to measure or quantify the mechanical properties for the part that has been exposed to CO2 and the one that has not been exposed to CO2. The second work package will be led by IFE. Actually, it will be led by me. And we have a lot of experimental equipment where a lot of autoclaves where we can inject supercritical CO2. So we will take an autoclave and fill it about 50% with a simulated brine and 50% with supercritical CO2. And then we expose the cement samples in these two connected but slightly different environments. And then we will study how this affects phase changes and microstructure. In addition, we will also have some parallel experiments where we add a lot of H2S to the CO2, and we will also try to simulate impurities, other type of impurities in the CO2 to study if that has an effect. So this will be a fairly complementary result to work package 1. The third work package will be led by the Technical University of Delft, by the Geo department, and they will study thermal cycling and how it potentially can lead to cracking in the cementing. This is a fairly simplified sketch, but they will use a cement plug with a pipe inside, and they will place this in a heated oil solution and then inject or pump a cooled liquid through the pipe in the center here to simulate a thermal shock situation. And this work includes one postdoc position, so we will have also some more academic contribution in this work package. The fourth work package will also be led by TU Delft, Microlab department, and they will use their simulation tools to do numerical studies of the microstructure, and they will focus particularly on this geopolymer sealant that is being developed in another work package. And also here there will be one postdoc position. Work package 5 will be led by the Heriot-Watt University, and they will study how these interfacial bonds between sealants and steel casing and sealant and host rock, how this is affected by CO2. And they have developed some, I don't really know the details of this, but it's some kind of electric impedance-based method that is non-destructive, and they will use this to monitor how this developed with time. Work package 6 will be led by the University of Stavanger, and they will use an existing geopolymer and try to modify it and optimize it for use for CCS wells. And this work will include one PhD student. It's another contribution to the academic work. And finally, the last work package will try to gather the results and information from all the other work packages and collect this and structure it and try to identify which key components or key properties do we need to ensure long-term integrity, and can we propose any suitable methods and procedures for testing, for instance. So we expect this project to give us an improved understanding of leakage pathways and to identify key properties for prevention of leakage. We will use 5 sealants in this project, but the principle and the testing methods can hopefully be used for future sealants. We think there will be a continuous development of new sealants, and for instance, that can have a smaller environmental footprint and still be improved. And we also hope that this can be used both for new wells and existing wells, and also for wells that is being plugged and abandoned. So I can try to answer any questions from you, but most likely you better ask Rainier because he's an expert on this. And you can follow us on social media. So thank you.
Thank you. Are there any questions to Gorte or to Anna or Maartje? I don't see Maartje anymore. Oh, there she is. Anyone? Maybe I have a question for Maartje, because the development of the tool, it's always a challenge, of course, to have a tool and to keep it updated. What's the plan of the project concerning that?
Yeah, that's a very interesting question, and indeed that discussion is something that we still need to have. How do we do this? Because we do want to have uptake. We do want people to actually use the tool. So at the moment I don't have a clear answer. What I can tell you is that within the consortium, but also outside, there is a very clear appetite to continue and to see if we could pursue this tool in whatever kind of way, to tailor it to something else, but to work on it, to continue to improve it. But we haven't figured out how to do so. Yeah, very valid question.
Yes, well, maybe a similar question could go to action.
Yeah, I think that our tool
You have to take the microphone.
I hope our tool is going to be used by people, and then because it's going to be open source, they will even have the opportunity to modify and tailor to their needs. So at the moment, this is what we have in mind to do.
Mm-hmm. Any other questions? I have a very organizational question. If there is somebody here from the Coca-Cola project that is going to present in 3/4 of an hour, please report to me. But because we are still we're lacking clarity whether there's somebody from Coca-Cola. Then, seeing that there are no questions, I would thank all the presenters in this session of Networks and Well Technology. There's a short break. We reconvene at 3. Please take the possibility to stretch your legs and take some fresh air. And I'll see you back.